Okay. Good morning, everyone. So today I'm going to start about water and its treatment unit, first unit. Okay. So unit one, water and its treatment. So when we are talking about water, first of all, so water it's a natural resource and it's a very important resource to everyone. And so it is called as a universal solvent. Why? Because it is a very essential to everyone. And water molecular formula is H2O. Okay. So then next, so what is the importance of water when we are talking about water importance? It is a very important, and it is then means we are using for a various purpose. So in industrial wise and in domestic wise, and for then means here industrial wise means textile industries, each and everything, and then domestic wise is washing, bathing purpose, like this. Okay, so then what are the sources of water here? Sources of water means mainly from rainwater. Okay, rainwater. So then here, then this rainwater is again two types: surface water and groundwater. So surface water is nothing but so which are present on surfaces. Examples for that means rivers and lakes. Groundwater, wells and springs. So then these are all the sources of water. And so then already I told, so importance of water. So living things, then each and everyone wants water. Why? Because it is a universal solvent and it's a very valuable, and it is a gift of our nature also. And so then why one can survive for weeks without food, but one can't survive only for few days without water. Okay, so it is a very essential for existing of a human being, animals and plants. Even most of animals and plants also contain a large portion of water. For example, in our human body, 70% of water is 75% of water is present in our human body. And land plants. So then plants also in aquatic plants, 95 to 99 percentage of water is present in animal, water plants. So like this, so then each and every, that means here consisting of water, some percentage of water. And this is also useful for other fields like production of, that means the pharmaceutical industry, cement industry, textile industry, washing, bathing purpose, each and everything. Okay, so then next, so then here hardness of water, so impurities. So then that source of water which is gifted by our nature, it is a not a pure water, it consisting lot of impurities. So impurities means they are all in presence, like dissolved impurities, and then it's consisting of dissolved gases and suspended impurities and biological microbial impurities also. So dissolved, when we are talking about dissolved impurities here, inorganic salts like sodium, potassium, and metals, chloride, sulfides, these are all present in a water. That means your our natural water resource, that is natural resource. No? So then these are all the impurities present in our water. And then dissolved gases. Which gases are present in water means oxygen, nitrogen, carbon dioxide, oxides, and so ammonia, hydrogen sulfide. These are all the present in our, these gases are present in our water. And suspended impurities. Suspended impurities is nothing but sand and clay particles and organic substances. These are all present in water. And coming to this microbial and biological means pathogenic microorganisms. If we are drink this type of then directly water without any that means your purification, so then we are going to sick. So that means pathogenic microorganisms are present in water. Then we are take that water directly to in our into our body. So then we face a lot of problems, and it's gives up, that means it's diseases. So arises many diseases. Okay, so like this. And then next next one is so when we are coming to this that means here hard water and soft water. So then here, when we are talking about, then two types of waters is there here. So then that is nothing but hard water and soft water. And what is the hard water and what is soft water? Okay, so then what is hard water and what is soft water? Hard water. Hard water means, so when we are, so see this. So this is nothing but hard water and soft water. Differences between hard water and soft water. Then hardness. First, before going to what is hard water, then what is the hardness of water? Hardness of water means, hardness in water is that nothing but it is a one of the characteristics. So then which is the one of the character for water which prevents the lather with soap. Okay. So then hardness in water is that the character which present in water, then which prevents the lathering of soap. Okay. So why? What is the reason here? Why it doesn't give a lather? So because of the presence of a calcium and magnesium and other heavy metal salts dissolved in it. Already previously I told, so a lot of impurities and dissolved salts are present in water. So due to especially calcium and magnesium, among all impurities, calcium and magnesium salts are very dangerous, and these calcium and magnesium and heavy dissolved metal dissolved salts are present in water. If they are present in water, then that water is a consisting of hardness character. Then that water is called as hard water. Okay, hardness is a property of a water. And what is a hard water means, the water which does not give a lather with the soap is nothing but hard water. So this is nothing but when we are applying hard water on for bathing purpose, or when we are applying the soap with the hard water, then what happened here? Then sodium is called as a, that means your calcium stearates, calcium soap. So calcium stearates. So sodium stearates is converted into calcium stearates, which is the white precipitate. Okay, it is a scum. So then it is called as a, so then means a white scum. So it gives a white precipitate. So then because of that, so then here then wastage of soap is takes place. And soft water means opposite to hard water, which gives a lather with soap readily, like this soap water. Okay, so then which that means soft water, which gives a lather readily with the soap. And then because of this, there is a no wastage of soap is takes place, like this. And then next, so here, so hard water we are not used for this purpose. This means here we are it is not fit for bathing purpose. And then here bathing and cooking purpose, and then here drinking purpose. So these are these hard water is not fit for these purposes. Okay, and then next, hardness of water. Already I told. So the property of water which does not gives a lather with soap is nothing but hardness of water. And then next, so this is nothing but hardness of water. And next one is here types of, when we are talking about types of hardness. Types of hardness means, so then two types of hardness is there: temporary hardness or carbonate hardness, permanent hardness or non-carbonate hardness. So temporary hardness. Then what is meant by temporary hardness? So temporary hardness means here two types of, already told, two types of hardness: temporary or carbonate. Means, so then if water, so then which is consisting of carbonates and bicarbonates. Okay, na? So in water, so then if the calcium and magnesium, which metal salts, calcium and magnesium, carbonates and bicarbonates, or if they are all present, these carbonates and bicarbonates are present in water, then that water is consisting temporary hardness. Then, so then here two carbonates, that means here carbonates and bicarbonates, they are all responsible for this hardness. So that's why this hardness is also called as carbonate hardness. Okay, so temporary hardness means temporary hardness due to the presence of carbonates and bicarbonates. And so because of this hardness is also called as carbonate hardness. And when these are, so magnesium bicarbonate, so that calcium hydroxide, like this, so then the magnesium hydroxide is formed here. Okay, so this is nothing but water. Then it is a temporary hardness. And permanent hardness or non-carbonate. So then permanent hardness means, so then here temporary hardness, it can be easily removed by the boiling. Okay, and permanent hardness. Permanent hardness is also called as non-carbonate hardness, Why? Because so then here the absence of carbonates. So none other than carbonate salts of calcium and magnesium are responsible for permanent hardness. So that's why it is called as non-carbonate hardness. And due to the presence of chlorides and sulfates of calcium and magnesium. So then which salts are responsible for permanent hardness? Calcium and magnesium. Chlorides and sulfates are responsible for permanent hardness. And because of absence of carbonates here, we are also called as non-carbonate hardness. So we are also called as a permanent hardness as non-carbonate hardness. And how can we calculate the total hardness in any water sample means? So then when we are combined both temporary and permanent hardness, so the sum of temporary and permanent hardness is gives a total hardness of water. So this is nothing but about types of hardness. Then coming to the units of hardness. So units of hardness, when we are talking about the units of hardness, expression on units of hardness. So here, then units of hardness means here 4 units are there for water. So then what are there means here? So first one is the parts per million, milligram per liter, and then degree Clark and degree French. 4 units are present. So then here units of hardness are 4 types. That means here parts of ppm, mg per liter, degree Clark and degree French. And these entire units are converted into in terms of calcium carbonate. So then hardness, especially we are expressed in terms of calcium carbonate. Why? Because so then calcium carbonate, it is a most insoluble salt. So then among all salts are present, all salts which are responsible for hardness, among all, we are expressed the hardness in terms of calcium carbonate. So then why? Because means there are 2 reasons for that. First reason is, so then calcium carbonate, its a molecular weight is 100. Molecular weight is 100 means it is a very useful to calculations purpose. Okay, and that is a first reason. And second one is it is a most insoluble salt in water when we are compared with the remaining salts. So that's why we are express the hardness of water in terms of calcium carbonate. And these 4 units are converted into calcium carbonate. So that are they, those are all ppm, milligram per liter, calcium, degree Clark, degree French. Here, what is a ppm? Parts per million. What is a ppm here means 1 ppm is equals to 1 part of CaCO3. Okay, if 1 part of CaCO3 is present in any water, then it is nothing but, so it is nothing but here considered as a 1 ppm. So 1 ppm is equals to 1 part of CaCO3 equivalence hardness present in a 10 power 6 parts of parts. 1 ppm nothing but 10 power 6 parts of parts. If 10 power 6 of parts we have to take in the 10 power 6 parts. So 1 part of CaCO3 is present, then that is nothing but ppm, parts per million. Then coming to this milligram per liter, 1 milligram per liter is equals to 1 mg of CaCO3. Means if when we are talking about milligrams, okay, so here relationship 1 liter. 1 liter in weights we are considered as 1 kilogram. Okay, 1 kilogram is nothing but here they mention milligram per liter. Okay, so we want these liters into, that means here milligrams means then these liters, 1 liter of liters is converted into weight means in terms of weight 1 liter water is equals to 1 kilogram. Then when this 1 kilogram is equals to how many grams? 1000 grams. So 1000 grams, when this 1000 grams is converted into milligrams means we have to multiply with the 1000. So 1000 into 1000. So then finally we got 10 power 6 milligrams. Okay. So then 1 milligram per liter is equals to 1 milligram of CaCO3 equivalence of hardness present in 1 liter of 1 liter of water. If 1 liter of water consisting 1 milligram of CaCO3, then it is called as a milligram per liter. And one here degree Clark, 1 degree Clark, that is equals to 1 part of CaCO3 equivalent hardness in 7000 parts. Here when we are considered 7000 parts of water, So in 7,000 parts of water, so if one part of CaCO3 is present, then it is called as a degree Clark. Okay, degree Clark. And so next one is degree French. So degree French is nothing but if 10, when we are taking 10 power 5 parts of water, in the 10 power 5 parts of water, if one part of CaCO3 is present, then it is called as degree French. So this is nothing but about a units. So then uh, what is the, that means here relationship between 4 units, among 4 units means 1 ppm is equals to 1 milligram per liter is equals to 0.07 degree Clark and 0.1 degree French. Okay, and then coming to this next, so then here estimation of hardness of water by EDTA. So then when we are talking about the hardness of water, so how can we estimate the hardness when we are taking one a sample, so water sample from any area, then how can we calculate the hardness in that water? Means, so the question, the answer for that question is this method, that is nothing but estimation of hardness of water by EDTA. Then this titration is also called as complexometric titration. Complexometric titration. Why we are called as the complexometric titration means here, so it is forms of complexes. So then here this is a complexometric method means where here we are using the ethylene EDTA means ethylene diamine tetraacetic acid. This is the structure of ethylene diamine acetic acid, EDTA. Then we are using as a reagent in this complexometric titration is EDTA. EDTA means ethylene diamine tetraacetic acid. Then it forms the complexes with the different metal ions. Why we are choosing this EDTA especially means, so it is a forms of complexes with the different metal ions. Okay, at a pH range 9 to 10 especially. Okay, so then that's why it is a that's why we are choosing EDTA. So when we are talking about complexometric titration, then definition, what is the definition of complexometric titration here means, then it is a formation of complexes. So formation of a complexes between metal and ligand. Okay, when metal and ligand, so here EDTA ligand is there, and metals where it is present in water in the form of calcium and magnesium. So then when these complexes is takes place between metal and ligand, okay, so then it is called as complexometric titration. So the titration which involve the formation of stable complexes between metal and ligand is called complexometric titration. Here we are using EDTA as a reagent in complexometric titration. Okay, EDTA means ethylene diamine tetraacetic acid. Why we are choose this EDTA means it forms metals, stable complexes. It forms the stable complexes with a different metal ions at a pH 9 to 10. So then it is also, what is the advantages? Why we are choosing this EDTA means it is a less consume and it gives accurate results. So that's why we are choosing EDTA. Then next. So then what is the principle involved in this method? What is the principle involved in this method means, when these are two basic principle is nothing but here, when to the hard water, okay, so hard water which is consisting calcium and magnesium ions, okay, so when this hard water is consisting calcium and magnesium, when we are adding EBT, here in this complexometric titration we are using EBT indicator. EBT indicator. In this titration, EBT is used as an indicator which is present in steel blue color. So hard water contains calcium and magnesium ions. Okay, when we are add EBT to water, hard water, which consisting calcium and magnesium. So here like this, calcium or magnesium, when we are add EBT plus EBT, it gives a unstable complex. That is this complex is present in wine red color. So either calcium EBT or magnesium EBT. So then when we are adding EBT to calcium and magnesium ions which are present in hard water, it forms the wine red color complex which is unstable complex. But what is our motto here? We want a stable complexes, formation of stable complexes. Okay, so then after that wine red color complex, so when we are add EDTA to EBT. So means here EBT means here when we are added EDTA, which is taken in a burette like this. So here titration. See here. So in titration in burette, we have to take a EDTA, and in conical flask, we have to take a hard water. Then this hard water, when we are adding EBTA, then it is forms unstable complexes with EBTA, who calcium and magnesium present in water. They are all forms a unstable complexes that which is in a wine red color. Okay, and when we are titrate this when we are titrate this wine red color against with EDTA, which is present in a burette, then this EBT is replaces with the EDTA. Then it forms the calcium and magnesium EDTA complex, and it can be a discharge EBT. Then the end point in this titration is nothing but blue color, which is the color of EBT. So what happened here when we are adding EDTA, when we are titrated EDTA against with the EBT complexes, then EDTA is replaces EBT complexes, and it is forms the stable complexes. Okay, so then the stable complex, then it is exhibits the EBT, discharge EBT into conical flask, that is a blue color. Then end point in this titration is from wine red color to blue color. Then next. So this is nothing but, so then this procedure, when we are, that is nothing but basic principle, and what actually takes place in EDTA, that is a procedure. Procedure involves three steps. First is a preparation of standard magnesium sulfate. Okay, preparation of standard magnesium sulfate is nothing but when we are taking 100 ml of standard flask like this, we have to take 100 ml standard flask, and in this so we have to take a 0.246 grams of magnesium sulfate crystals. Okay, so we are taking 100 ml standard flask. What is the procedure here? We are prepared standard solution. Standard solution means known concentration. For what? For how much? Means 100 ml of MgSO4 is prepared here. So we have to take 100 ml standard flask. In this 100 ml standard flask, we have to transfer 0.246 grams of magnesium sulfate into 100 ml standard flask, and to this add distilled water, a little amount of distilled water, up to, then means we have to add little bit amount of MgSO4. Then it is a dissolved completely. After that, this water is make up to the mark, then it is considered as 100 ml solution, standard solution. So it is prepared for 100 ml, so standard solution of MgSO4. Then that is the first step. And second step is here standardization of EDTA. So means here we have to take one conical flask. Okay, conical flask. In this conical flask, we have to take a standard MgSO4, which is prepared in a first step. So standard MgSO4 means 100 ml standard MgSO4. So then this MgSO4 is taken in a conical flask. Okay, and then next to this add, what we have to add here means we have to add indicator, which is the EBT. So exactly 2 drops of EBT is added to water, standard MgSO4, and to this we have to add 5 ml of ammonia buffer. It's a very important here. Why we are adding ammonia buffer here means, so then already I told EDTA is a forms of stable complexes with metal ions at the pH range 9 to 10. So to maintain the stable pH, in a solution, so we have to add ammonia buffer. This is actually basic buffer. Ammonia buffer means sodium chloride plus sodium hydroxide. Okay, so then this is nothing but second step, standardization of EDTA. We have to take conical flask and take 10 ml of MgSO4, which is prepared in previous step, and to this add 2 drops of EBT and add 5 ml of ammonia buffer. This is the second step. And third step, next titration. So step 2, after we have to do the titration. So in titration, we have to take a EDTA in a burette, and in conical flask already step 2 solutions are present in a previous step 2, and we have to take a burette. Then this burette is filled with EDTA up to mark and titrated against with the conical flask. Okay, so then this here in previous step. So then when we are add these all type of ammonia buffer EBT, then it is in wine red color, which is of EBT is a forms of unstable complex with the calcium and magnesium that is present in wine red color. And this wine red color solution is titrated against with EDTA, which is present in burette. Then wine red color solution is converted into blue color solution. Okay, blue color. This is a nothing but end point. End point color is nothing but indicator color. Blue color indicator EBT is present in blue color. No, so then winded. What is the end point? Winded color to blue color. What happened when this color changes from winded to blue color means here EDTA is replaces EBT, and it can be exhibit the EBT into solution into conical flask. That's why then the end point is nothing but the color of EBT. And next, so then here repeat this titration with 2 times to get a concurrent values. Concurrent values means same values, and note down same as in your tabular column like this. And we have to calculate the M1 molarity. M1V1 is equals to M2V2. Then here from this step M1 molarity of MgSO4 we got then means here weight by molecular weight into 1000 by 100, and volume how much we have to take 10 ml, and molarity of EDTA is going to be determined now. And V2 volume of EDTA, how much of volume is consumed here in this that means your titration, that is volume of EDTA. Then you have to substitute each and everything. Then we are got a that means M2 here. Okay, now so that is M2 is equals to M1V1 by V2. So then when we are substituting that that means your concern values, then we are got a so then we will get molarity of EDTA. And next, so step 3, this is the final step. So then we have to estimate the hardness of water here. So then total hardness of water. Okay, so then in step 3 we have to take instead of we have to take a conical flask. So in this conical flask, instead of a standard MgSO4, we have to take a tap water directly. So 10 ml of tap water we have to take in a conical flask in third step. And to this same as mentioned in previous, so we have to add indicator, 2 drops of indicator EBT, and 5 ml of ammonia buffer, which is acts as a buffer. Means buffer, it is by adding buffer it maintain the pH from 9 to 10. So then this solution, then conical flask solution is titrated against with the EDTA solution, which is present in a burette. Then again same end point is from wine red color to blue color. Okay, so then this is nothing but third step. And so this is nothing but here colors. So first of all, when we are that means here add EBT, then it is in a wine red color. Then end point is a blue color. Okay, pale blue color. And next one. So then your calculation. So then here also step 3 also repeated for 2 times or 3 times to get a concurrent values, and note down that values in this tabular column. So initial and final, and how much of volume of EDTA is consumed here. And from previous step already we know M2. Okay, now we are going to determine M3 molarity of water. So from this molarity of water, then total hardness is revealed here. Okay, and then here M2V2 is equals to M3V3. We want M3 here, molarity of water. Then M3 is equals to M2V2 by V3. So already we know M2 value, which is that came in a previous step, M2 molarity of EDTA. You have to substitute in place of M2. And V2 volume of EDTA, how much of volume of EDTA is consumed, then titrating values you have to substitute in place of V2. And V3 volume of water, how much of volume of water we have to take, 10 ml of hard water, tap water is directly taken in a conical flask. We have to substitute 10 ml in place of V3. Then finally you will get M3. M3 is nothing but molarity of water. So finally, then total hardness of water is so calculated here like this. So M4 is equals to molarity of water is equals to then M4 is equals to molarity. Then permanent hardness. So total hardness we will get we will get total hardness. Now that is nothing but M3. Then M4. M4 means here molarity of water is equals to what we, how can we find M4 into 100 into 1000. Okay. So then here then finally we will get M4 here permanent hardness. So here permanent hardness means then result. So then temporary hardness of water. So first of all here total we are reveal total water here. So then from this total hardness, so then temporary hardness of water and permanent hardness of water is also revealed by using this formula. Total hardness is equals to temporary plus permanent. So when we are when we want temporary, then total minus permanent. When we want permanent, total minus temporary. Then it comes in a ppm. So at finally, then here by using of complexometric titration, by using EDTA method, we will estimate the hardness of water in any sample. Then, so that is nothing but complexometric titration. And next topic is, so then here internal treatment of a boiler feed water, softening of or conditioning methods of hot water. And then here softening of water, softening or conditioning. How can we softening or conditioning of hard water? There are two methods is there to softening or conditioning. So already I told lot of impurities are present in that water. Then we can't use that water directly. Okay, so then before you have to use, we have to condition or softening that hard water. So then there are two types of waters is there. Okay, so it is a mandatory already told. So before going to use any water, you have to pure that water. You have to softening that water, and we have to remove each and every impurities from water. After that, we have to use. So for that purpose, here two methods are employed here to softening the water. They are all external treatment and internal treatment. So now let us discuss about external and internal treatment. So here like this. So lot of methods are there in softening of water, like geolite process, ion exchange. Here in internal treatment, colloidal conditioning, phosphate conditioning, carbonate, colgan, and so treatment of sodium aluminate. So then these two, so there are two, again I repeat, so two types of methods are there to softening of water. One is external and another one is internal. So external treatments means geolite process and ion exchange. And internal treatment means colloidal conditioning, phosphate conditioning, and carbonate conditioning, like this. Okay. So now we are going to discuss about these two methods. First one, external and both external and internal. Now, so internal treatment. What is internal treatment actually? So what is internal treatment means here? So the treatment which is gives to water. So before it is taken into any that means your devices. So for example, here we are using a boiler. That means boilers. So a lot of boilers means which is used for the steam generation. Steam generation purpose, we are using boilers here, especially. So in this boiler, so then internal treatment means before going to take that water into boiler, fed into boiler, we have to, that means you're conditioning the water. Then what is the internal treatment? What is the internal treatment means here? So internal treatment of water is nothing but the softening of water. That softening of water carried out inside the boilers. Inside the boilers, for example, we have to take a boilers here. So in boiler feed water, how can we treat that conditioning that water means? So when we are taking that water into boiler, so the treatment which is carried out inside the water only, inside the boiler only, then that is nothing but internal treatment or internal conditioning. So it can be a, what is the internal conditioning here? We have to, in this method, we have to add chemicals directly to water which is present in boilers for removing the dangerous scales formations, sludges formations. So these are all takes place in water. and then these are all that means here leads to boiler corrosion and very dangerous to boiler. So then when we are fed that water into boiler, within the boiler we have to treat that water by adding chemicals. So this is nothing but internal treatment. Why? Because why it is called as internal means it is carried out inside the boiler, okay, within the boiler. So that's why it is called as internal treatment. Okay, so then this method especially used to convert the scales and sludges. So in because of that means the dissolved salts present in water, scales and sludges are forms in water. Then especially in boiler feed water, then these scales and sludges are that means converted into that means you're in easy form to remove by blowdown operation. So that is nothing but internal treatment here. And next, so internal treatment, there are three types of internal treatments are there. First one is phosphate conditioning, second one Colgan, and third one colloidal conditioning. So let us discuss about one by one. So then Colgan conditioning. So then first of all, Colgan conditioning. What is meant by Colgan? Colgan means calcium gone. So entire calcium gone in a water, hard water. So colgan is the scientific name for colgan is sodium hexametaphosphate. Sodium hexametaphosphate. Then the formula is Na2 Na4 PO3 taken 6 times. So sodium hexametaphosphate is called as colgan. Why it is termed as colgan means calcium gone, means entire calcium will be removed like this. So then this interacts with then here what happened when this colgan is added within boiler. In boiler, inside boiler water is there, no? So inside that boiler we have to add this colgan, means sodium hexametaphosphate to boiler feed water. Then it forms the highly soluble complex like this, sodium hexametaphosphate. Okay, instead of calcium, then here, sorry, instead of here in colgan, instead of sodium, then calcium is replaces here sodium. So then calcium hexametaphosphate is formed here, and along with the sodium sulfate. Then here Na2Ca2PO3 taken twice. Then which is a calcium hexametaphosphate? It is a soluble in water. Okay, then soluble in water means it is easily removed by using a blowdown operation, and there is a no problem with this formation of calcium hexametaphosphate in boiler, and it is a soluble in water, so automatically we remove this that means within a boiler from by using blowdown operation. So colgan conditioning is a it's a very better than phosphate conditioning. Next, phosphate conditioning. So then here scale and sludges, already told scales and sludges are formed because of dissolved salts present in water inside the boiler water. Okay, then phosphate conditioning, here scale formation. Scale formation can be avoided. Okay, scale is it's a very dangerous to that means here boiler. It is a very hard and adherent that means adherent on the inner walls of the boiler, and it is a very difficult to remove. So to remove of scale from boiler feed water, we have to use the phosphate conditioning here. Then scale formation. Scale formation, it can be avoided by adding a sodium phosphate here. Okay, in high pressure boilers. Then when we are, what happened when this sodium phosphate is added to water means, so it is forms the sodium phosphate is converted into calcium phosphate. Calcium phosphate. Then it is a very easy to remove. Then so here then three types of phosphates are usually employed here. One is trisodium phosphate, disodium phosphate, monosodium dihydrogen phosphate. So then depending upon our priority, we have to use these three types of phosphates. So then if the boiler feed water is too acidic, then we have to employ trisodium phosphate. If boiler feed water is weakly acidic, we have to employ disodium hydrogen phosphate. Why? Because it is in weakly alkaline in nature. So that's why we are adding, if the boiler water is weakly acidic in nature, so we have to add disodium hydrogen phosphate, which is weakly alkaline in nature. Okay, and then if the boiler feed water is that means here acidic, so the alkaline water. If it is in a slightly basic in nature, then we have to employ so monosodium dihydrogen phosphate. So depending upon the nature of the boiler feed water, if it is alkaline or if it is a basic, or if it is a weakly alkaline, weakly basic, depending upon this nature of boiler feed water, we have to choose these three types of phosphate. So among all three types of phosphate, trisodium phosphate is a employed. It's employed in a high way. So why? Because means here trisodium phosphate, it's employed in a lot of situations. Why? Because it forms the stable complexes, and with whom calcium and magnesium metal ions. So trisodium phosphate forms a stable complexes with the metal ions. That is the one reason, and it at a pH range, pH 9 to 10. It maintain the pH also. It maintain pH from 9 to 10. Why? Because at that pH only metal ions forms a stable complexes. So then then it is a, so trisodium phosphate is a maintained pH, so 9 to 10. So that's why it forms a stable complexes. So then among three phosphates, we are employed for boiler feed water, especially for boiler feed water, in high amount in a, so that means your high percentage trisodium phosphate. And then next conditioning is nothing but colloidal conditioning. Colloidal conditioning means here colloidals, so formation of colloidals. Example for colloidal means nothing but milk, it's I mentioned. So colloidal here also, then in boiler feed water, we have to by adding some chemicals, so we have to that means remove the scales and sludges formation. So then what is the colloidal conditioning means here? Means in colloidal conditioning, so which type of chemicals are going to be added here? Means corrosion, kerosene, agar-agar, and gelatin. Kerosene, agar-agar, gelatin. Then these are all the chemicals which are added to boiler feed water in a colloidal conditioning. When we are add these chemicals to boiler feed water, then this it forms the colloids. So colloids, these are all especially used in low pressure boilers. Then when we are then these form of colloids with that water, then it is a here like this. Then this converted scale, then in here a scale formation, especially scale formation is removed by this method. So then these substances like calcium carbonate, calcium sulfate, these are all then scales are converted into sludges in this conditioning. So why? Because scales are very difficult to remove, no? So then that's why then by adding these chemicals to boiler feed water, scales are converted into sludges. And which can be then sludges. Why? Because sludges, it's a easily removed. Why? Because these are all loose and non-slimy substances. So then scales, so adherent substances are converted into loose and slimy substances. That is, scale is converted into sludge. Then it can be removed easily by blow down operation. So this is nothing but colloidal conditioning. So then these three conditionings are belongs to internal conditioning, internal treatment or conditioning of water. So by usage of these three conditions, we are that means we are remove scales and sludges in boiler feed water. This is belongs to internal treatment. Means why? Because it is takes place inside the boiler. Inside the boiler, we have to add different types of chemicals, and these scales are converted into sludges. Then finally, we remove these sludges by blow down operation easily. So this is nothing but internal treatment. Then when we are coming to the external treatment means here so ion exchange already I told. So internal treatment means here internal treatment, colloidal conditioning, phosphate, and that means here phosphate, colloidal conditioning. Then these three conditionings are comes under internal conditioning. And external conditioning is nothing but ion exchange process. Then what is ion exchange process here? So external, that means here before going to that means here process. So then what is meant by ion exchange process? Ion exchange processes belongs to external treatment of water. Then what is meant by external treatment? So the treatment which is gives to boiler, then before it is fed into boiler. So then means outside the boiler. Internal treatment is inside the boiler. It takes place inside the boiler. Then external treatments means so the water, the treatment which is carried out outside of the boiler. Then after that, then that water is fed into boiler feed or boilers. So the treatment which is gives to water before it is fed into boiler is nothing but that means nothing but external treatment of water. So this ion exchange process is belongs to external treatment of water. So then what is meant by ion exchange here? What is meant by ion exchange process, and how can we that means remove the salts in by using of this external treatment? Means here in this ion exchange process, then two types of resins are present. Here we have to, in this ion exchange, we have to take a resins means two types of resins are employed here. One is cation resins and anion resins. Why we are taking these two means we are remove entire cations and anions of metal ions present in water. So here two types of resins. First one is cation exchange resin, anion exchange resin. Then these two are employed here. Then these are all that means your these resins are microporous structures with a long polymeric chain structure. Okay, then it's consisting of microporous structures. These are all the polymers. Then here, so what is the process here actually? Here means when we are take that raw water which consisting impurities, then that is directly fed into that means here in a first chamber. First chamber is nothing but it's consisting cation exchange resin, and second chamber is that means consist anion exchange resin. First of all, raw water, when this raw water is fed into, that means here into first chamber, which consisting of cation exchange resin. Okay, like this cation exchange resin. And what happened when this raw water is enter into cation exchange resin? Then this already I told these are all the polymers which consisting of microporous structures. So then the cations which are present in water, then that can be retained by the cations of exchanger resin. Here ion exchange means so cations of the cations of the water metal water that means here calcium or magnesium, calcium +2 and magnesium +2. So then cations of water is exchanged with the cation of resin. Here that is nothing but ion exchange here. Ion exchange. So ion exchange takes place with the between water and resins. So water cations are exchanged with the water resins cations. So here when this raw water is entered into first chamber, that is cation exchange resin. So here then the calcium Ca+2, magnesium +2 like this. Then cations which are present in water that can be exchanged by the cation exchange here. Then here cation exchange resins means nothing but it consisting of H plus ions, especially functional groups as a acidic functional groups. Anion exchanges consisting basic functional groups. So here acidic functional groups are responsible for the exchange of cations with their with their cations with water cations. So water cations are exchanged here with the cations of resin like this. And so then coming to this next one, what are the reactions which takes place during this during this process is nothing but here. First of all here, okay, so first of all like this. So when we are talking about here that means RH2 RH is a formula of a cation exchange resin. So these are all acidic groups. When this NaCl where it is present in water, when this NaCl, for example, NaCl we have to take. So when NaCl is reacts with the RH, then it is a form. So that means here exchange of cations or takes place here. So water who is water cation here? Na plus. And who is resin cation? H plus. So here RNA plus HCl is formed. So that means in place of H in a cation exchange resin, sodium is replaces. Sodium is replaces the H place. Oh, so that's why RNA plus HCl is formed here. So then here that the water which is comes from the first chamber, it is a highly acidic in nature. Why? Because of the formation of HCl like this. HCl is formed here. So that's why the water which is comes from first chamber, it is a very highly acidic in nature because of the formation of HCl. And then this water which is in a high acidic nature enter into the second chamber. So which is nothing but anion exchange resin. This anion exchange resin is consisting of basic functional groups. So that's why when this raw water, that means acidic nature water, which is comes from first chamber, enter into the second chamber. Then here in first chamber, all cations which are present in water is removed. Then our responsibility here means, so we have to remove both cations and anions. In first chamber, cations are removed, and when this water is entered into second chamber, all anions present in water are removed. Okay, so here then here that the metal that the water anions are exchanged with the resin anions here. So then these are all that means exchanges takes place. Finally, then what happened here means, so here finally here H plus and OH minus ions, then it finally gives the water here. So H plus ions, where it is comes from? So then H plus ions is comes from first chamber, and OH minus ions is comes from second chamber. So then H plus and OH minus ions both are combined, and it is releases the water, pure water without any dissolved salts. Why? Because entire cations and anions are removed here. So by the exchange of cation and anion exchange resin. So then this process is also called as demineralized process. Why it is called as demineralization means, so entire minerals which are present in water is removed. So that's why it is called as deionized, without absence of ions and absence of minerals. So that's why it is also called as demineralized or deionized process. So this is nothing but so ion exchange. And so then by the usage of these two resins, gradually these are all going to be exhausted. So we want these cation and anion exchange resins for the next that means purification. So for that purpose, again we have to that means retain this cation and anion exchange resins. We have to generate again for the next process. Then how can we regeneration of cation and anion exchange resin means, so here, then this chamber is it can be attached with the dilute HCl. Then this dilute HCl is enter into this chamber. Like we have to that means here passes this dilute HCl into first chamber. Then again, then what happened here means regeneration of resin takes place. And here also cation, anion. So when we are adding NaOH, dilute NaOH to anion exchange resin, so again, this anion exchange resin is also regenerated. So by adding dilute HCl to cation, by adding dilute NaOH to anion exchange resins, again we have to regenerate the cation and anion exchange resin. So which is useful for the next process, next purification of water. So this is nothing but about ion exchange. And next, so coming to this potable water. So this is the last topic. So then what is the potable water here means, so then the potable water and then the specifications of potable water and steps involved in potable water. Okay, so then potable water here, what is meant by potable water first? So the potable water is nothing but it is the water which is used and which is fit for human consumption is nothing but potable water. According to WHO, World Health Organization, and ICMR and BIS, so they are all they give us some specifications to potable water. If that specific, then those WHO and these three organizations, So if they are give us some specifications to water, if any water is that can be consisting that type of specification, that water is considered as potable water. Okay, so potable water is nothing but potable means it is a Greek word, so which is from Greek language. So then what is a potable means it is edible to drinking purpose. Okay, so then definition, what is definition here? So potable water, the water which is fit for human consumption is nothing but, that is nothing but potable water. And so then here, these are all specifications. Specifications of that means characters of drinking water. What are the characters of drinking water? Pure water means then that drinking water should be colorless, and then pleasant odor. It consisting pleasant odor, and turbidity is a 5, and then pH value is a 6.5 to 8.5. These are all the characters of a drinking water. And next, drinking of potable water. Next, so then total hardness must be 300. If this total hardness value is exceed 300, then it is considered as a hard water and it is not fit for human consumption. And then next, then the steps. So this is nothing but potable water. Then where this comes from means our GHMC is that means your supply this potable water for each and every the door to door domestic purpose. Okay, so then these are all the steps which are followed by GHMC to purify the rainwater, and then which is a supply for human consumption. Okay, so then these are all the steps. First of all, sources of water, screening, aeration, sedimentation, coagulation, filtration, and disinfectation. So first of all, first step is nothing but here. First, so then water treatment. So first of all, it's here. This is the flow chart of water. Potable water steps. First one is the raw water, coagulation, flocculation, sedimentation, and next filtration, and then so treated water storage, and finally then they supply to domestic, that means door to door, that is for human consumption. So first of all, so then water source. So we have to, they are all, that means store this rainwater at some, that means reservoirs are present in GHMC. So they are all reserve that water, rainwater. So they are directly, that rainwater is comes to that tanks. So some reserve tanks is there. So then that rainwater is present in that tanks. So enter into that tanks. Next, so next step, what is the next step means here? So already told. So then here, so first of all, screening here. Second step, sources of water means the rainwater. Rainwater is enters into the tanks, large tanks, which are that means here present in a GHMC. So then that's water is enter into the tanks. Then after that, then first step is nothing but screening here. Screening. What is a screening here means? So then. Screening here. So screening, so then what happened here means they are that means here allotted a big screens. So a lot of that means big screens are present in a that means here GHMC. Then they are all made up of with the steel. So then what happened when this water, then water is passes through these screens. So when this water, so the raw water, when raw water is passes through the that means your screens. So screens, then floating matter. So not only the impurities but also each and everything is removed from water. So here first of all in screening, so then water is enter into this that means through these screens, then floating materials are removed in this screening. And then next step is aeration. Aeration means we have to remove the gases which are present in water. Then gases are, they can be exchange with each other, and then aeration. In this aeration, then exchange of gases are takes place. So gases are removed. And then sedimentation. And then next one is a sedimentation. So then here from screening, So floating materials are removed. Floating materials like wood pieces, leaves, and so then papers, whatever it may be, they are all removed during this screening. And then after screening, it is entered into aeration. Here, that means your gases which are aeration, the water then subjected to aeration. It can be helps in exchange of gases between water and air. So then it can be increases the oxygen content of the air. And if it is any iron, manganese, these impurities are present in water, they can be removed in aeration step. And coming to this sedimentation step, sedimentation here means like this, sedimentation. So sedimentation along with the coagulation. See this here. Sedimentation and coagulation means, so the suspended and colloidal impurities. So suspended and colloidal impurities are removed in this process. Okay.